rate data that you can analyze. And I think it makes more sense to do it along with catalysis because it's going to be rate data about catalysis. So it made more sense to kind of delay that. And it's not something I can test you on anyways very easily, you know, analyzing rate data. Usually done in Excel, right? So that'll be the third little unit, which will be catalysis and rate data, yeah.
Is the final cumulative?
Yes. Yeah, it's not, otherwise it would just be on catalysis, and you guys do not want that. Okay, so heat effects. All right, so let's say that we have some PFR. We have A goes to B, but now we're operating it. So what's changing along the length of the reactor? What else?
Concentration.
Conversion or concentrations. What else? Could be. So this is really more for a packed bed reactor. Most PFRs we assume more or less no pressure drop. But if I fill it with a solid, now I really got to worry about the change in pressure. Because this is changing, I also have to worry that my rate constants are changing. Yeah. So what is changing the temperature of the reaction? What property of the reaction is changing the temperature within the reactor itself? Exothermic or endothermic. Yeah, we call that the delta H of reaction, right? So it's the enthalpy either consumed or released whenever a chemical event happens. It's related to, but not, the activation barrier, right? I can put them both on one diagram. Which one is this? If this is reactants, transition states, products. This energy difference is, yeah, the delta H of reaction. This energy difference is the delta H of activation. Generally speaking, although it's not always true, if I decrease the delta H of reaction, what do you guys think happens to the barrier? Increase, decrease, stay the same. Doesn't increase, it's going to decrease. Now again, that's not always true, but it's often true, because if I'm stabilizing this by some mechanism, then I'm likely also going to stabilize to a similar, but to less extent, I'll also stabilize the transition state, because this transition state is going to look chemically like my product. It also, of course, looks chemically like my reactant, but it looks more like my product than my reactant, right? It's further along the reaction coordinate. So it's going to look more like my product than my reactant. So if I find a way to stabilize the products, this will often come down, so the barrier also will decrease. It's not, again, it's not always true, but it is something that you observe a lot when you're trying to design catalysts. Okay, so the delta H, a reaction will either release or consume energy to change the temperature. So our design equation for a PFR right? And now the rate is a function of what? Concentration, as it always has been, but now it's also a function of temperature. So that means that dx dv is a function of conversion, which is concentration, and temperature. And of course, if the concentration is also a function of pressure, then I could also have pressure in here as well, if pressure's changing. So what did we do when we had pressure drop? How did we solve the problem? Did we still use the design equation? Yeah, that was one of the equations. So when we had pressure drop, we used this design equation, which was that the change in concentration with the mass of the catalyst is equal to the rate over, that's it, just the rate. And because concentration is a function of pressure and rate is a function of concentration as well, you got a function, if I write it in terms of conversion, yeah?
Are you assuming that the change in temperature is not going to affect activation energy?
That's a good question. Technically speaking, temperature does change in activation energy, but it's a small change. It changes a lot, the rate constant. And that's why when we write out the Arrhenius equation, right, K is equal to some pre-exponential factor times the exponent of the activation energy over RT. We're usually assuming that that's constant. But in reality, it's not, but it changes just a small amount. And that's why we can write, we can observe for many, many, many reactions. If I plot the inverse temperature versus the log of the rate constant, you get a straight line. Because the activation energy, which is the slope, isn't changing. But some reactions, you'll see a slight curve. That's because the activation energy is actually changing over that temperature range. All right, so we had one equation which was a function of conversion and pressure. What was the other equation that we had to use then? And that allowed us to write a second equation, which was the change in pressure with changing catalyst mass as a function of conversion and pressure. And then how do we solve those? You could make a big assumption, which will allow you to write this out in a much more convenient way. Or you can solve the system of coupled ordinary differential equations. It's not easy to do. You won't be asked to do that on the test, but you can do it. You've theoretically been taught it before in your COT course. Theoretically. But yeah, there are numerical methods by which we can solve differential equations, right? And so you can apply one of those numerical methods to the system of two differential equations, and you can get a solution. And that's what, if you're looking in the book, that's what Polymath does. That software that he keeps trying to get you to buy. He must get $10 for everybody who buys this $30 software. But yeah, that's what that does. It just solves it numerically. Okay, so just like over here, we use the Ergun equation. Now what do we need to do? What's another equation that we can use? So we need some equation that relates temperature to conversion. So what equation might we need to use? First chemical engineering course you guys took.
ETDZ?
No, you're thinking about transport, which unfortunately, we're not even there yet. Fortunately, I should say. Material and energy balances, right? We've done a material balance. That's all that this is. These design equations are just material balances. Except now you're generating things, whereas in that course, the generation term was always 0. Now we need to use energy balances. And we have to solve the material and the energy balance simultaneously. We have some flow in, and now what did we use to represent heat transport in MEB? And you have some work that's being applied within the system. Imagine this is a CSTR, right? So I could have an impeller, and then I have things flowing out. And in addition, you have heat transfer in or out of the reactor. So we have this nice thing that helps us. Right, just like we had in the conservation of mass. So we see that the change in the energy of the system with time is equal to Q minus WS